All right, our next speaker is Professor Olek from Purdue. His presentation today is the effect of nano-additives on hydration behavior and the durability of concrete containing fly ash. Please join me to welcome Professor Olek.
Well, good morning, everyone. Thank you for being here. It's the last day of the conference, so it's always difficult to get the audience, but we are more appreciative than ever for you being here. So I want to talk about some of the work that we've done for the Indiana Department of Transportation. They were looking at the ways of improving the performance of fly ash containing concretes during the winter operations. Indiana used to have a ban on using the fly ash in concrete that was placed between 1st of October and end of April of the next year because of the concerns that low temperature will slow down the hydration of concrete that has a fly ash, and during the application of the de-icing salts in particular, that there might be excessive scaling, which is commonly reported for concretes that contain the supplementary cementitious materials, especially the fly ashes. But over the years, we've learned that actually using fly ash in concrete is very beneficial with respect to preventing the damage due to the oxychloride formation in the joints of concrete pavements. So right now, DOT says we just have to be careful, but we are allowing to use the fly ash all year long. So that was sort of a motivation for this particular research topic. So I'll talk a little bit about the background. I actually already did. Then I'll talk about materials and methods, some of the results and discussion. So as I mentioned, long-term durability of concrete that contains the fly ash is definitely enhanced, but the slow strength development, especially at early ages, and we have very often a situation that the bridge decks or approaches to the bridge decks and so forth are placed late November, early December, and if they contain the fly ash, as they would right now, is there going to be a problem long term because of the slower strength development. So one of the nanomaterials that we tried to incorporate was titanium dioxide. The other nanomaterials that we tried were colloidal silica. I will talk mostly about titanium dioxide with a little bit of information about colloidal nanosilica. So we were comparing concretes that were plain concretes and concrete containing fly ash. And fly ash was replaced at 24%. Cement was replaced using 24% by weight of fly ash. It was class C fly ash. And we use essentially 3 levels of addition of nanotitanium dioxide, as you can see here, 0.5%, 1%, and 2%. And we also did curing at 2 different temperatures. One was at the standard temperature of 70 degrees Fahrenheit, and the other one was at low 40 degrees Fahrenheit to try to simulate the behavior that the concrete may be experiencing during the low temperature construction season. We've done a number of tests. I will just report on some of them here. So we were looking at the contribution of the nanomaterials to kinetics of hydration, looking at the isothermal calorimetry, looking at the amount of hydration product using a TGA, and then we used various techniques to assess the durability of concretes that contain those additives, and that included determining the volume of permeable porosity, water absorption, scaling resistance. We also did freezing and thawing resistance, but I don't have time to report on that here. So as you know, TGA allows you to examine the phases that are present in the hydrated cement paste by exposing it to the heating conditions, and progressively the material will lose water, and you can capture the amount of water lost and associate it with the amount of phases that the water was present in, so that would be mostly CSH and calcium hydroxide and other phases like ethringite and monosulfate and so forth. In other words, some sort of an indicator of the degree of hydration. We did that at 3, 7, and 28 days. We used the procedure that is described here. We stopped the hydration at certain age by using isopropanol, and then we crushed the samples, dried it briefly, crushed it, and performed the analysis in TGA instrument. And if you look at the sort of a typical curve that you will get, so this is illustrated here, so you see progressive loss of mass due to the decomposition of the phases and driving of the water, and you can see in the table what processes or what phases are losing water at the given range of temperatures. So we are losing the capillary water first, then we have dehydration of gypsum, we'll start losing bound water from CSH, and finally, there are 400, we are starting the composition of the calcium hydroxide. So what we did, we look at the total weight loss up to about 450 roughly degrees Celsius, and associated that weight loss with use it as an indicator of amount of hydration that happened. So it's sort of an indirect way of determining the degree of hydration, if you will. The higher the number, the higher the weight loss, will indicate that we had more phases that were losing the water, means that the hydration level was higher. Okay, so this is the total amount of water loss that we were concerned with, and some results that we got from that. You can see on this slide 0%, that means there was no nano titanium dioxide added, and then we have bars for 0.5, 1, and 2%. This is for P, which means plain concrete, no fly ash added. And you can see at various ages, addition of nano titanium dioxide increases the amount of hydrated phases as indicated by TGA. If you, that was for the room temperature. If you look at the low temperature, you can see a pretty significant increase in the amount of hydrated phases. So definitely, even in plain concrete, when the concrete is cured at low temperature, adding nanomaterials helps you with increasing the degree of hydration. When you look at the concrete with the addition of the fly ash, you can see very similar trends. In this case, we've seen the increases both at 7 and 28 days, and also obviously at low temperature. The other method that we used was isothermal calorimetry. So that gives you information more about the kinetics of hydration and how quickly the material starts reacting, and what is the total heat output that is associated with the intensity of the reaction, if you will. So we excluded about 45 minutes of the data that we got from isothermal calorimeter because of the need for equilibration. But afterwards, what we've done is we put our material in the glass vial, put in the isothermal calorimeter, and what you get from there is rate of heat development and total heat. So those are the general shapes of the curves that you will observe. And if you look at the results for the plain paste, you can see that 22 degrees we have certain behavior, and if you look at the magnified version near the top of the peak there, you can see slight differences resulting from the addition of various percentages of nano titanium dioxide. The general trend that you can observe is that as we increase the amount of nano titanium dioxide, we are increasing the height of the peak, and we are shifting it to the left, meaning that we have a higher heat output and it happens earlier. So there is some acceleration of hydration, which kind of confirms the data from TGA that I showed you before. So the top graph was for 23 degrees Celsius. This one is 4 degrees Celsius or 40 degrees Fahrenheit, low temperature curing. And again, you can see a similar behavior. We have the acceleration of hydration. And listed in the table is the relative shift of the maximum temperature peak, both at 23 and 4 degrees Celsius. And you can see in particular at low temperature we have much more significant acceleration of hydration. So conclusion is that adding nanomaterials does increase the heat output, and kinetics of hydration is generally accelerated. When we look at the fly ash containing paste, we see a very similar behavior at both temperature, both room and low temperature, and you can see the relative shifts. They are a little bit higher than they were in the case of plain concrete. So the conclusion is that if you are using nanomaterials, the acceleration that you get in the systems that contain fly ashes is even more significant than it is in the case of the plain concrete. We look at the porosity of the material. Now that we know that we have this acceleration of the hydration, what does it do to the microstructure of concrete, and would that help with durability characteristics? So porosity and permeability be one of those properties that we'll be interested in improving. So we look at the total amount of permeable porosity following the ASHTO-TP135 process. You essentially calculate the porosity using this equation, and you can see some of the results summarized in here. So we have AP and AF. This is two series of concrete, P being a plain concrete with no additions of any nanomaterials. Sorry, P being a concrete without the fly ash, with various nanomaterials being added to it, F being a concrete with fly ash, with various amount of types of nanomaterials being added. And then we have also another concrete, which we increase the water cement ratio a little bit because some of the nanomaterials that we are adding, nano-silica, required a little bit higher water cement ratio in order to be able to maintain the workability. And again, we've done it at two different temperatures, 23 and 4 degrees Celsius. And total volume of porosity, if you look at the last column of this table, you will find out that there's not maybe very significant reduction in porosity, but nevertheless, essentially for all of those materials, you will see the reduction in porosity. In this series, we also incorporated this nano-silica. You can see the numbers there, like 12, 8, and 4. Those are the ounces per 100 pounds of cement that admixture was added. So we were adding 12 ounces. So those were liquid admixtures, nano-silica dispersed in liquid solution. That's how it's being supplied. So we added either 12. There was a combination of 2 of them, or 8 for this particular one called LFA. It stands for liquid fly ash. That's how they market it. And 4 ounces, that's for internal cure. That's how the manufacturer markets that. So the addition of both of those nanomaterials, titanium dioxide and nano-silica, reduced the porosity. Well, I guess that stopped working. Well, this doesn't show very well. Yeah. Oh, I am terrible with the mouse. All right. So let's move on to the next one. So this is the indication of the reduction in porosity, and you can see by addition of nanomaterials, we are able to reduce the porosity of both plain concrete, those with the red bars, and the fly ash concrete, that will be the green bars. So it is particularly effective, the addition of these materials in concrete that contain the fly ashes. And we go back to what I showed you on the kinetics of hydration and the amount of hydration product. They were very effective in accelerating the hydration of the fly ash containing concrete. Then we also look at the absorption that's related to the connectivity of the pores and also obviously to porosity. So if you follow the standard ASTM-C 1585, you cut the discs from the cylinders, you precondition them in a certain way and expose one surface to the water sorption essentially. So that's how the specimen looks like. We modified the procedure a little bit. The ASTM standard asks you to dry the specimens at 50 degrees and then follow it by 15 days of conditioning in sealed container. But we repeatedly found out that you don't get the linear behavior in the, during the absorption process, the amount of water absorbed versus square root of time. And that's actually a requirement. You have to have R-square value of about 0.98 or 98% for the test to be valid. And we couldn't get it because that process for this material did not result in emptying of the capillary porosity. So we are not the first one who experienced that. People do various modifications. What we've done is, we dried it 60 degrees and we essentially conditioned it to the constant mass, which was defined as daily mass change of less than 0.2%. And that worked well. So if you look at the slopes of those curves, in this region, and they look pretty linear, right? This is maybe slightly curved, but still pretty linear. But what I wanted to focus our attention on is, the curves that are sort of a cross-hatched symbols. Those were with the addition of nanotitanium dioxide, and you can see they are all below the solid line, which was the plain concrete without the addition of nanotitanium dioxide. And those work very well, meaning that we depressed the position of those, meaning that we have a lower absorption rate. And on the right, you can see the same information for concrete that contain nano-silica, and that also worked well. And this is at low temperature, the same kind of behavior. We have a linear behavior, and we have a reduction in the rate of absorption for both nano-silica and titanium dioxide. You can see that here. And this is sort of a summary of the total absorption, both secondary and initial absorption. Initial absorption has to do with the amount of water that goes into the capillary porosity. Secondary absorption is more related to diffusion of the moisture into the pore system. But you can see that at both temperature, addition of nanomaterials reduce that, and especially if you look at the green bars, that was very effective for concretes that contain the fly ash. So that's the bullet points summarizing that. And very similar observation for materials that contain the nano-silica, the relative reductions were a little bit lower in this case. But nevertheless, it was also effective. And finally, I wanted to show a little bit of data on scaling resistance. So DOT insisted that we make a concrete that has a composition that would be typical for highway pavement application. That requires the presence of about 6.5 plus minus 1.5% of entrained air. So in principle, if the air entraining works well, you should not have a problem with scaling. And so we've done that, and you can see that the overall appearance of the surface of the specimen after 50 cycles of freezing and thawing doesn't really indicate a great degree of scaling. We see a slight improvement upon addition of nanomaterials, in this case nano-titanium dioxide, 0.5% and 1%, and if anything, maybe if you add 1%, you have a little bit worse behavior. The 1 and 2, those are the relative ratings of the scaling severity based on the standard. We also were looking at the Canadian standard. Ontario Ministry of Transportation has this criterion that if your scaling is less than 0.8 kilograms of mass loss per square meter, then you have no scaling problems. And all of those specimens were way below that, so we really didn't have scaling problems. When you look at the addition of titanium dioxide for fly ash concrete, you can see that we have a little bit more scaling at 0% addition. That's what I was telling you earlier, that the use of the fly ash typically results in a little bit higher scaling. And 0.5% didn't make it worse, for sure. Adding like 1% of titanium dioxide for room temperature cure looks like it makes it worse. We get the rating of 4. But if we do it at, when we look at the surface of concrete that was cured at low temperature before exposure to scaling tests, that was about 3 at this point. So again, the overall mass losses were not very high in this case. And if you look a little bit more quantitatively on what was happening, you can see that fly ash concrete was scaling a little bit more, but adding about 0.5% of titanium dioxide helped it a little bit. Adding 1% definitely did not help. We're still not sure why there is this maximum effect in case of the amount of nano-titanium dioxide added, but nevertheless, it did exist, as you can see over here. And very similar trend at 4 degrees Celsius as well. So we have a situation where may improve the scaling resistance, but you have to be careful as to what amount you use in order to not make it worse. To conclude, we saw improvements in rate of hydration and improvements in the degree of hydration, but upon addition of these nanomaterials, in particular in concretes that contain the fly ash. That was related to the acceleration of hydration in the presence of those materials. We saw a reduction in the water absorption, reduction in the rate of water absorption, and we've seen some improvements in the scaling resistance. So this is all I have. There's some of these of the references that I was referring to on the introductory slides, and with that, I will thank you for your attention, and we'll be happy to answer any questions you may have. Thank you.